All right, welcome to video 3.5. We're getting close to wrapping up chapter 3 here. We'll talk about the percent composition in empirical formulas. And really this is getting at this basic question, which is how do we actually experimentally determine the chemical formula of particular chemical compounds. We're going to pivot a little bit away from limiting reagent and yield for a second, but we'll use some of the same stoichiometric tools to get to these answers. Okay, so the field of chemistry, typically, if we have an unknown compound and we don't know what it is, we use a tool to figure out what that is. And so in this case, we'd use this tool here called CH Analyzer, which we have in the chemistry department at Colorado College. What we can do is take a little bit of the sample, we'll say this is the sample, tiny, tiny, tiny bit, and we know it exactly. We know the mass to maybe 6 significant figures. We load it into this thing and we combust it. And after that combustion, we'll get some result that might look something like this. It tells us, well, your unknown white substance was 84% carbon and 15.9% hydrogen by mass. And so we need to take this information given to us by this tool, this instrument, the CH Analyzer, and we need to convert that into a molecular formula. And so hopefully you're saying, well, I can't simply say that this thing is carbon 84, hydrogen 15.9. Why can't I say that? Think about this, pause the video for a second and say, why does that not make sense? Okay, so hopefully you thought about it for a second. The reason is compound, just like in a balanced chemical reaction, a compound, let's say H2O, that 2 here is a stoichiometric relationship that says 2 hydrogens for every 1 oxygen bound. It has no bearing on the mass of those things. It doesn't say that 2 grams of hydrogen are present for every 1 gram of oxygen. We know that because the atomic weights of these things are not necessarily proportional. So if we've determined this by mass to be 84% to 15.9%, that's not the same thing as moles. So we need to get these numbers into moles before we can get a formula that's actually a true molecular formula. So don't make this mistake on quizzes and exams. It feels like it's intuitive, but it's not. We need to get to moles before we can do anything. Okay, to do that, the simplest way is to just assume, even if this isn't true, just assume that your sample is 100 grams. Doesn't matter. You can assume any mass, in fact, and this will still work. 100 just makes the numbers easier since we're working in percentages here. So let's start by assuming 100 grams. If we do that, then that means that our sample is 84 grams of carbon, and it also means that our sample is 15.9 grams hydrogen. Okay, that makes it really simple because then we can just go through and do some dimensional analysis with the atomic weights of these things and figure out how many moles that equates to. So we know that if we look at the periodic table, there's 12.01 grams of carbon for every 1 mole of carbon. So we can solve that. We can do the same thing with hydrogen. We can say 1.008 grams of hydrogen for every 1 mole of hydrogen, and we can compute these numbers. And so we get roughly 7 moles of carbon, and we get 15.8 moles of hydrogen. Okay, so does that mean that our compound now is carbon 7.0, hydrogen 15.8? Not exactly, but we're getting closer. It at least tells us that the ratios of these things are 7 to 15.8. And so the next step we need to do is just get these into divisible whole number multiples. And so simplest way to do is just divide by the smallest number in the molar ratios. In this case, this is 7, and we'll divide both sides by 7. And so when we do that, that gives us this new compound with carbon 1, H 2.26. So we know that there's not such thing as a 0.26 hydrogen atom. You either have a whole one or you don't. And so the last sort of step here is to figure out the smallest whole number multiple that makes these full digits. And so you can see that this 0.26 is pretty darn close to a 0.25 or a quarter. So we can multiply this whole thing by a factor of 4, and what we get from this is C4H9. And this number, I'm sure you're thinking to yourself, well, that's not exactly 2.25. Nothing is perfect in science. We're going to get numbers that are pretty close, but our ultimate formula has to be whole number ratios. And so most often you will get numbers that are either close to a quarter like this, or maybe it's like C1H2.5, which is pretty obvious, or maybe it's C1H2.33, in which you'd multiply this by 3, or you multiply this one by 2. I won't give you anything that's really, really tricky to figure out. So in this case, what we've just deduced here is that the simplest relationship, if we just go all the way back to our original data, our simplest molar relationship between carbon and hydrogen in this molecule is 4 to 9, C4H9. This is not necessarily the final molecular formula. It's close, but we call this the empirical formula. And we call it the empirical formula because the word empirical literally means experimental. And so this is the experimentally determined formula. We don't really know if this is exactly it, but we do know that in the real formula, we'll still have the same ratio of 4 to 9. We just don't know if this is C4H9 or perhaps it's C8H18 or some other variation of that. To get the true molecular formula, I'm going to rotate this up a little bit. To get the true molecular formula, we need to also know the molecular weight of the compound. And so often what we have is 2 experimental methods that we use in tandem. So as chemists, we do that with this nice fancy tool called a mass spectrometer. A mass spectrometer is an expensive tool. We have many of them on campus, in fact. This is a particularly expensive one. This is not one we have. But it allows us to measure the mass of individual molecules, which is a really, really powerful technique. And so with the CH analyzer at the beginning, we get the percent carbon and the percent hydrogen. And with the mass spectrometer, we get the experimental molecular weight of the compound. Okay, so how do we actually get to the final molecular formula having this piece of information and this piece of information, the empirical formula? Well, if, for example, in this particular example, the C4H9, if we took that molecule and we figured out that it weighed 114.2 grams per mole, well, then all we have to do is figure out, well, how much does this thing weigh, and does it weigh the same thing? Or does it weigh some fraction of it? And so if we look at the empirical formula, which I often just call the empirical weight, EW, we can compute that. We just add that up. So we take 12.011 times 4 for the carbons plus 9 times 1.008, and we get an empirical weight of roughly 57.1 grams per mole. Okay, so that means our molecule that we empirically determined is actually lighter than what we determined using the mass spectrometer. If you look at these numbers, they're an exact ratio of each other. And so what we can do is we can figure out, we can take the molecular weight divided by the empirical weight, in this case 114.2 over 57.1, and that's going to give me a factor of 2, which means that the actual true molecule is 2 times the mass of this one, in which case we can take that 2 and multiply it by our C4H9, which our empirical formula gave us, and that's going to give us our true molecular compound, which is C8H18. Okay, so that's how we determine the true molecular formula. I'll talk in a little bit about how and what data looks like from a mass spectrometer so that you can interpret that. So while we're at it, let's just run this exact same process but in reverse, because sometimes you know the molecular formula, but then you want to figure out how much mass percent is composed in that particular compound. So let's do this for this common compound that you have all likely experienced before called aspirin. let's see, aspirin, and that has a molecular formula of C9H8O4. Okay, so we've got the molecular formula and we want to figure out by mass what its composition is. So the exact opposite of what we'd done before. Okay, so this is pretty straightforward. I'm going to scroll up here a little bit. And we can do this with dimensional analysis and stoichiometry, and we can say that for every 1 mole of this aspirin compound, there, let's say for 1 mole, we've got 1 mole aspirin, that's got 9 moles of carbon, right? Because for every 1 of those aspirin, it actually has 9 moles of carbon inside of it. And we can say that for every 1 mole of carbon, there's 12.011 grams of carbon. So we can do this quick dimensional analysis. This gives us 108 grams of carbon. We can do this for hydrogen and oxygen. I'll do that really quick. Okay, so I just knocked that out for hydrogen and oxygen the same way. So for 1 mole of that aspirin, we've got 8 moles of hydrogen in this case. Each mole of hydrogen weighs 1.008 grams. So that equates to this 8.08 grams of hydrogen. We've got 108 grams of carbon. Same thing for oxygen. This is a 4 here if you can't read that. That gives us 64 grams of oxygen. I can add all these things up, or I could have just computed the molecular weight in the common way, and that gives us 180 grams. So now we know of that 180 grams, how much of it is carbon, how much of it is hydrogen, and how much is oxygen. And so we can simply go through and say that to get the percent by mass, 108 divided by 180 times 100%, the 8.08 divided by 180 times 100%, and the 64.0 over 180 times 100% will give us our mass ratios of each of those, which come out to 60.0%, 4.49%, and 35.6%. This isn't something we do often, but it's sometimes nice to know for various reasons what the actual weight percentage is of your particular compound relative to each of the individual elements. But it's more common to actually go the opposite direction, where you have an unknown compound, you know its percent by mass by using a CH analyzer, and you need to use that to work out what is the molecular formula, which is what we did just a couple minutes ago. So if you don't have a CH analyzer, we can also just burn the substance in oxygen using what's called combustion analysis. And this is also a really common technique. And it produces almost the same data, but it requires maybe one additional step to determine the ultimate empirical formula for a substance. So for instance, we could take methane gas and burn that in oxygen, and that would produce CO2 and water. And it's important to note that in any combustion reaction that uses oxygen as an input and some hydrocarbon like CH4, you will always produce a mixture of CO2 and H2O. In this case, the balanced chemical reaction would be a 2 there and a 2 there. Okay, so if this thing is unknown, but we know that we can add oxygen, and we somehow can build a tool that measures how much CO2 and hydrogen or water are produced, we can work backwards using stoichiometry to deduce what the ultimate unknown compound is. And so we're going to use some of the tools that we've used before, but it's really very similar to what we did just a couple minutes previous. Okay, so we've got sort of a perfect example here. This is coming out of your textbook. It states that we've got this thing called caprylic acid, which we don't know and we're not meant to know. We're trying to figure out what it is. And we have 0.450 grams of it, and that's the sample we have, and we're going to combust it in oxygen, as mentioned before, to yield 0.418 grams of water and 1.023 grams of CO2. And we need to use this information to first determine what the empirical formula is, so that's the sort of simplest representation. And if we know the molecular weight, then we can use the empirical formula to then determine the molecular formula. So let's work this step by step. Okay, so what I did was just write out a generic chemical reaction. We don't know how to balance this because we actually don't know what the molecular formula of caproic acid is, but I can write this out because I know in a generic combustion reaction, which is what we have, I'll always be burning some hydrocarbon in the presence of oxygen, and I'm going to yield water and CO2. And I know that I burned 0.450 grams of caproic acid in oxygen, and I yielded 0.418 grams of water and 1.023 grams of CO2. Okay, so I'm just sort of setting up the problem so I can see it in a more linear way. So the first step I want to do is find the molar amounts of carbon and hydrogen in the caproic acid sample. So how do I do that? Because all I know are the masses of water and CO2. Okay, so this is it requires sort of a key leap of faith for us. So how do we get to the amount of carbon and hydrogen in the sample? Well, we can look at CO2 first. And we can say, well, we know the mass of CO2 that's produced. Could we figure out the moles of CO2 or moles of carbon that are produced? And the answer is yes, because we know that for every 1 mole of CO2, that yields 1 mole of carbon. But this is where the real leap of faith comes in. We know that in the reactant side, so everything on this side of the reaction, the only possible source of carbon in the overall reaction has to be coming from caproic acid, right? Because we're mixing it with oxygen gas, which is just pure O2. So if we're yielding CO2 with carbon, that carbon must be coming from caproic acid. So if we can figure out the number of moles of carbon in the CO2, that's going to be the same as the moles of carbon in the caproic acid. So that's our first step. And sort of by analogy, we can do the same thing with H2O. We can say, well, there's no hydrogen coming from the oxygen on the reactant side. It has to be coming from caproic acid, which means we can figure out the moles of hydrogen coming from H2O, so we'll figure out moles of H, and we know that there's a sort of 2-to-1 relationship here. There's 2 of these H's coming from every one of the caproic acid, and so we can figure that out. So let's do this step by step. Let's say first, let's do moles of carbon, and so we'll set this up as 1.023 grams of CO2 is produced. I need the molecular weight of CO2, which is 44.01 grams of CO2 for every 1 mole of CO2. And I also know that then for every 1 mole of CO2, I have 1 mole of carbon inside of that molecule, right? So I can get rid of these units, and what I'm left with is 0.02324 moles of carbon, which is this number, which is also this number. That's how many moles of carbon are in the original caproic acid sample. Okay, so we can do the same thing for moles of hydrogen, and I'm going to just do that really quick, and then you can follow along. Okay, so using the same process, I've got the 0.418 grams of H2O that's produced. So I'm starting with that value, that's 0.418 grams H2O. I know the molecular weight of H2O is 18.02 grams for every mole of it. So I can cross out those grams in moles. So for every 1 mole of H2O here, though, I'm producing 2 moles of hydrogen. And that's crucial because I've got this 2 here. And that's what's different between moles of carbon and moles of CO2. Those were 1-to-1 because that's just CO2. In the case of hydrogen, there's 2 of those for every 1 unit of H2O. And so that's going to produce a value of 0.0469 moles of H, which, because hydrogen can only be coming from the caproic acid, that's also the moles of H in the caproic acid. So we're working our way through this. Let's move on to the next step. So we know the number of moles of carbon and hydrogen in the original caproic acid sample. What we need to find out now are just the number of grams, which is easy because we just need to convert using the atomic weights of carbon and hydrogen. So we can figure out the mass of carbon, which would be the 0.02324 moles of carbon. So that's coming from this value here. And we can say for every 1 mole of carbon, there must be 12.01 grams of carbon in that sample, which equates to 0.2791 grams of carbon. And that again is in the sample, in the original caproic acid sample. We could do the same thing for moles of hydrogen. So we can say that that's 0.0469 moles hydrogen. For a mole of hydrogen, we've got 1.008 grams of it. Let's set that, and that gives us 0.0469 grams of hydrogen in the original sample. Okay, so we're getting pretty close here. So if we think this through, remember in the original problem, we were told that we had a sample, that was the white powder that we analyzed, that was 0.450 grams. So we had that original sample, and we just figured out that of the 0.450 grams, 0.791 grams of it is carbon, and 0.0469 grams of it is hydrogen. Okay, so what we want to do now is figure out, well, is our sample purely made up of carbon and hydrogen? If that's the case, then these two numbers added together should also give us the total mass of the sample. So let's take 0.450 grams and let's subtract 0.2791 grams. So that's the mass of carbon, that's the mass of the original sample, and let's also subtract then 0.0469 grams, which is the mass of hydrogen. And what that gives us is 0.124 grams of leftover. So what is this stuff? Well, it's not carbon and hydrogen. So what else could it be? Well, we got to figure that out. Okay, so in most cases, you're going to be dealing with compounds that are made up of carbon, hydrogen, and oxygen. You'll be told that in the problem. It doesn't always have to be the case. In this case, the problem, it didn't say explicitly, I meant to mention it to you, but this problem was just carbon, hydrogen, and oxygen. And so, since we know there's oxygen in the problem, then this has to be, whatever this leftover mass is, it has to be coming from oxygen. And so that's pretty straightforward then. We just need to figure out the moles of oxygen. So if this leftover is mass of O in grams, then we can say that 0.124 grams of O, and there are 16.00 grams of oxygen for every mole of it. That's going to give us 0.00775 moles of oxygen in our final compound. Okay, so we've been going back and forth, grams and moles, grams and moles. So let's figure out this sort of final step. Okay, so just like we did with percent composition in previous problems, we know that we have a certain number of moles of carbon, hydrogen, and oxygen. So we can write these out in a really simplified version of the molecular formula. So carbon, we figured out, had 0.02324 moles. Hydrogen, we'd computed 0.0469 moles. And oxygen, we'd computed 0.00775 moles, which came from this most recent calculation. And we'd already determined that we can't have fractional numbers of atoms in the overall molecule, and so what we'd done before in the percent composition case was just divide all of these by the smallest number to try to get whole number multiples. In that case, the smallest number is the 0.0075. So let's divide all of our numbers here by that 0.0775. And let's see what that gets us. So that's going to yield this C3H6O. Okay, so that's a nice whole number ratio. Remember, this isn't necessarily the actual molecular formula, but this is the empirical or the experimental formula of the compound. And if you go back to the original question, remember that it asked us to figure out what the actual molecular formula was, and it told us that the molecular weight of the compound was measured with mass spectrometry to be 116.2 grams per mole. Okay, so we know what the sort of empirical formula is. We know the weight of the actual molecule. So remember that in order to actually evaluate whether or not this is the molecular formula, we need to add up the mass of this thing. So if we look at the mass of this, we called that earlier the empirical weight. We can add up 3 times 12 plus 6 times 1 plus 16. That'll give us the total molecular weight, or the empirical weight of this compound, which gives us roughly 58.1 grams per mole. So these two things are not the same. So that means this empirical formula is not the same as the molecular formula. But remember, all we had to do was take the molecular weight divided by the empirical weight, get some factor here, which was 116.2 over 58.1, and what we get is this nice whole number of 2.0. Again, we can multiply that by our original empirical formula, and we get C6H12O2 as our final molecular formula. So that's a lot of work, but this is a really good example of a real chemical problem, right? Using stoichiometry, using percent composition, using the concept of the mole, grams, conversion factors. People use this all the time in chemistry, where they take an unknown powder that they've created in their flask, and they've got this stuff, they put it into a CH analyzer, they get some percent carbon and hydrogen, they put it into a mass spectrometer, and they get some molecular weight. These two things together, if we utilize this step-by-step process, can give us the actual molecular formula, which is pretty striking, right? We've got these macroscopic tools that humans can push buttons and run and ultimately deduce the molecular ratios of carbon, hydrogen, and oxygen in this substance that's impossible to see. So it's a pretty powerful technique. So work through this, work through the several examples that are in your book, in the suggested problems, and in the worksheet. We'll certainly ask you this on probably a graded workshop or a quiz or something like that.